So far, we were focusing on exact matches, which will help us to answer the question where the positions on my genome and in the reference genomes are identical. But we, of course, are most interested in approximate pattern matching because we want to find positions in my genome that are different from the reference genome. An approximate pattern matching problem is given a string pattern, a string text, and an integer d. We try to find all positions in text where the string pattern appears as a substring with at most d mismatches. I'm sure you can come up with a fast algorithm for solving this problem, but I'm really interested in a more difficult problem, multiply approximate pattern matching. A set of string patterns, a string text, and an integer d is an input, and we want to find all positions in text where a string from patterns appears as a substring with at most d mismatches. Let's try to use the Burrows-Wheeler transform again to find approximate matches of Anna in Panama bananas, and we will allow up to one mutation in Anna. We'll start again with finding all rows in the Burrows-Wheeler matrix that start with Anna. Here they are, and among them we want to find rows that contains NA. And among 6 rows that start with A, only 3 of them actually end with N. Here are these rows, and we are interested in them. They form exact matching of the last 2 symbols of Anna to our text. But that's not the only thing we are interested in. In the past it was the only thing, but now we are actually interested in all 6 rows starting from A because we are interested in approximate matches as well. And to find approximate matches, we need to retain all these 6 rows and specify the number of mismatches for each of these rows. Here they are. After we found all rows we are interested in, we use again the first last property to find where the symbol in the last elements of these rows appear in the first column, and they will be appearing here. Once again, we check which of these 6 appearances will match Anna with at most one mutation, and it turns out that one of them actually doesn't satisfy this property because there is a match, but it's a match with 2 mutations, which is beyond our maximum allowable number of mutations, and that's why we are not interested in this row anymore. And then, by applying class to first property again, we find all occurrences of Anna with up to 1 mutation in text. How do we find where all these 5 approximate occurrences appear in the text? We can use suffix array, or more precisely, the partial suffix array, and you can figure out how to use the partial suffix array to find approximate occurrences as well. I tried to hide some details of approximate pattern matching with Burrows-Wheeler transform to make it a little bit easier for you to understand how it works. In reality, it is a bit more complex. If you wanted to learn about the details of approximate pattern matching with Burrows-Wheeler transform, you can find these details in our bioinformatics algorithm course on Coursera or in our book. Sam Burns had a very rare genetic disease. In fact, there are less than 1,000 people on Earth with this progeria. However, there are over 7,000 of such rare genetic diseases, and as a result, about 10% of human population have a rare genetic disease. We now learned how pattern matching will help the doctors of the future to learn about mutations in our genome and will allow them to diagnose many of these mutations. However, even if a child is diagnosed with a disease-causing mutation, in the case of progeria, there is no cure. And this is the next challenge for personalized genomics, moving from diagnostic to new drugs aimed at specific diseases. And to finish this lecture, I will tell you just about one case of a very successful drug that biologists developed based on exact knowledge of specific mutation implicated in a disease. I will talk about a more complex type of mutations. So far we talk about a point mutation when one nucleotide is changing into another nucleotide. But there are more complex mutations that work as an earthquake operating on the genome. In this particular case, I'm talking about so-called Philadelphia chromosome that is formed from two normal human chromosomes. Pieces of this two normal chromosome exchange position. As a result, two chimeric chromosomes are formed as shown here. Biologists figured out how to detect this event, and it turned out that it is a biomarker for chronic myeloid leukemia. And based on exact knowledge of biological mechanisms, admittedly it's more complex than the mutations we studied, but it's once again a mutation in the human genome, biologists were able to develop a miracle drug called Gleevec that is very efficient for chronic myeloid leukemia.